Hi Judith, I'm Chandramouli, the TU for this course. So let's get started with problems related to this week's assignment. So as you can see, um, I have prepared some questions. Let's start with it, and then we can clear your doubts as well. All right?
Okay, sir.
Is it fine, Judith?
Yes, sir.
Okay. So let's get started. Okay, let me share my screen. Is it my screen visible?
Yes, sir.
Okay. All right. So now let's get started. Okay. So can you see the question and tell me how to solve this problem? So basically, this week's assignment includes kind of all the problems that have been brought to throughout the class. So based on that, we'll be dealing with problems. So they have given a function and they've told that this is the total derivative. Okay? They're telling that this is the total derivative. So now, so what they're asking is that whether this could be a total derivative or not is what they're asking us. So how do we find that? How do you find that, Julie? Given, let's say a function is given, and it's in terms of b and t. How do you write the total derivative?
Here, can we explain with exact differentiation?
Yeah. We have to check if they are exact differentials or not. Okay, correct. So how do we check that? Condition to check is
Del
they
P, del F, del V equal to del F, del P.
correct. So this should be equal to right, this is the condition, right? Condition to be satisfied.
Yes.
Yeah. Condition to be satisfied. Okay. So now, first, what is our del f by del v? That is 2n rt by v minus nv whole square. So which implies this del by del t of del f by del v is equal to just 2nr, and so the t goes because of differential. So this is the value here. And then if we take del f by del t, the value is r v minus nv by nv square. Okay, so that's all. So if we do, this equal to r divided by nv square. And as you can see, both these are not equal. Correct.
Yes.
So that's quite evident. So basically, we'll just write it down. 12 square. I'll just write it. It's not equal to 12 square. So that means it's not a total derivative, not a total derivative. Okay, fine. So we have the answer here. Quite easy, straightforward. So you're clear with this, right?
Yes, sir.
Okay. So the next question is, we have thermodynamic cycle, and then we have a PV graph of the thermodynamic cycle. They're asking us to find the total work performed during this thermodynamic cycle. So how do we do that? And there are two ways. Whichever way you have done, that's fine. But which one do you, I mean, do you know how to do that? Let's see. Which way you have done, JV? You can do it two ways. You tell me the two ways that we can do. Okay, so what is the work done formula? First, you tell me that. Hello. JV, can you tell me the work done formula?
Yes, sir.
Yeah. What's the work done formula?
W equal to FD.
That's force into displacement, correct? But in terms of in thermodynamics and pressure and volume, what's the work done? Minus PdV, right? Or minus
Yes,
P
sir.
delta V, whichever way. Huh? Okay. So now we can do it in two ways. If you calculate the area within this path, then that is the work done. That's as simple as that. We can do it another way also. Total work done. Work total is equal to pathwise we can calculate AB plus BC plus CD plus DA. So if you see here, you see the path here. AB, in this AB path, is there any volume change?
No, sir.
So then that means work done is going to be 0, right?
Yes.
So that is 0. Similarly, in path CD also, volume change is 0, so work done is 0. So we have only work done at BC. So that is P external at B. I'll just put PV. PB into volume at C minus volume at B plus minus PD and volume at A minus volume at D. Alright, so this is clear, right? This is a P external, volume at C minus volume at B. Similarly for this path, volume at A minus volume at D. Correct. Now, what are the values? Minus 300. This is an atmosphere, okay? 300 atmosphere. And this is in centimeter cube. So Vc minus V, 2 minus 1. This is in centimeter cube. Really plus minus 100 atmosphere. Here again it is 1 minus 2 centimeter cube So it is minus 300 plus 100 equal to minus 200 liter atmosphere. Sorry, not liter. Atmosphere, centimeter cubed atmosphere. Centimeter cubed atmosphere. So we need to first convert it to liter atmosphere, then to joules. Okay. So what is the conversion factor? How many liter is equal to say one? How many centimeter cube is one liter? 1 centimeter. 1 liter is equal to how many meter cubes? 1000 liter is equal to 1 meter cube. I think I'm correct there. Just check once. Yes. 1000 liter is equal to 1 meter cube. That means so it's going to be how many centimeter cubes? So it's 10 power 3 liters. 10 power minus 2 centimeter. Sorry, 10 power 2 centimeter. Correct. For 3 liters. So 1 centimeter cube is equal to 10 power minus 3 liter. So minus 200 into 10 power minus 3 liter. Okay. So that's how much is it? 0.2 liter. Correct. So this is the total work done. So we want this in joules, right? So how much is 1 liter? Liter atmosphere to joules conversion. Okay, 1 liter atmosphere is 103. 1 liter atmosphere. 1 liter atmosphere is equal to 101.3 joules. Therefore, total work done. And just multiply that. How much is it? Minus 10 to right. 10, so
20.26.
sorry,
20.26.
20.26.
Yeah.
Okay. 20.6 joules. That is our final answer. Okay. I know in the assignment it is in kilocal. You convert it to kilocal. Per conversion, I guess you can do it. Fine. Okay, Zvi? You understood? Did you
Yes, sir.
understand this? Yeah. Okay, so let's go to the next problem. So you tell me how to solve this problem. How do you think we can solve this problem? So you know that U, internal energy, is a natural variable of S and V, right? We'll leave N for now. S and V, right? Correct.
Yes, sir.
So that means du, okay, du can be written as constant plus P Q Q as constant. So we can write like this, no? And from work done and heat formula, we also know that du is equal to TdS minus PdV. Correct. All right.
Yes.
So now, which means del U by del V at constant pressure, sorry, constant entropy is minus 1. Fine. So this we know. Okay. Now what we'll do is they have given us the entropy, sorry, internal energies formula. V square plus 4 plus V square. So this is the internal energy value. So we need to calculate the pressure value, because you see they are asking us enthalpy, which is a variable of pressure and entropy. Okay, so we need to know the pressure value. So let's calculate the pressure value. So how will we get pressure value? We need to take the derivative of this with respect to V at constant S. So since S is constant, this is 0, so it will become 2V, which implies minus P is equal to 2V, or V is equal to minus P by 2. So this is the volume value. Now we'll calculate the enthalpy. So enthalpy, as we spoke before, enthalpy is a natural variable of pressure and entropy, and also number of particles. Right now we are considering only one particle, so let's leave that out. And also, you know the formula, right? Enthalpy is equal to what? You tell in terms of U and PV. What is the formula? H is equal to U plus PV, right? So this is the enthalpy formula. So U is already given. What is the U value? 2s square plus 4 plus V square. 2 square plus 4 plus V square plus PV. Now we'll convert all the V in terms of P, because we want everything in terms of P, right? P and S. So 2s square plus 4 plus minus P by 2 square. Okay. V is equal to minus P by 2, correct? Plus P2 minus P by 2. Let's just do this. Square by 4 minus P square by 2. So finally, enthalpy in terms of P and S equal to 2s square plus 4 minus P square by 4. So this is the final formula for you. Okay. Did you understand this, Devi?
Yes.
Okay. Do you have any doubts here? First, we need to find out the pressure value from the equation itself, equation of internal energy itself, by comparing TdS and minus PdV to some differential form, then calculate the differentiate U with respect to V at constant entropy to get P. That's what we did here. And then we used enthalpy formula H is equal to U plus PV to get the final equation. All right?
Yes.
Okay. So now next question is, we need to calculate the Joule-Thomson coefficient in terms of Cp alpha known quantities. So do you have any idea how to do this? First, you tell me the formula that you know for Joule-Thomson's coefficient. What is Joule-Thomson's coefficient? At constant enthalpy, we see the change in temperature as we change the pressure. Okay, so this is Joule-Thomson coefficient. Fine. This is the standard definition. Now we need to find out, change this into some variable such that they are all measurable quantities. So P, Cp, alpha, all these are measurable quantities. That's what we need to do. Some manipulations we have to do. So let's start doing it. Did you go through the lecture? Last week you told me you didn't go through the lectures for Jacobian relations and all. Did you go through it?
Yes, sir.
Okay. Then we are using Jacobian method for transformation. So this is how we can write this as a Jacobian. Now what we'll do is we will introduce another multiply and divide by another variable. Okay. So what we're going to multiply and divide by is E. Okay. I'll use what I'm using. I'll use SNP. Yeah. I'm using SNP so that I can get values I can get values differential such that I can use Maxwell equation. So that's why I'm using it. Now we'll write it like this. D comma comma B then B nothing. So this comes here and this goes here. Fine. So now I want P to this side so that I can write it easily. So when I do this, when I invert it, it's gone. There's going to be a minus sign over it. Okay. There's going to be a minus sign on. One more thing one more thing I'll do here. I will also bring H this side so that becomes the main variable. Okay. I'm bringing H this side, so this will also be minus into minus del P del PH. So this is what we have. So minus minus will get cancelled, so that is quite straightforward. Then let's expand this. One more step before that. So this is going to be, what I'm going to do is del HT and del SP. Here, what I'm going to do is I'm going to do one more step. I'm going to bring this to the denominator. Okay. So what happens is this will become like this. Okay. Just going into reciprocal and using the reciprocal. It's minus because this comes below. Okay, minus. That's why I have put like this. Now let's expand this. Expand this. So what is this? This is basically a determinant, right? So del H by del S constant pressure. And similarly, this will be del H by del P next at constant. See, I did S and P because they are natural variables of H, and now you can see that H and S we are getting quite easily, and these will be like we can directly see the equation of enthalpy and get these values. So that is why I used S and P. Then del T del constant. So this is a determinant. And this will be del H by del S constant. and this is going to be inverse. Now what we'll do is we will see this equation. Okay. Now what I'm going to do is I will write the total differential of enthalpy. See, enthalpy, as I told before, it's a natural variable of S and P. Okay, so which implies dH is equal to del H by del S constant P ds plus del H by del P constant S dP. So this, as you know, from normal formula, it is TdS plus VdP. Okay, fine. So from these to compare these two, we will see that del H by del S at constant P is equal to temperature. Similarly, del H by del P at constant S is equal to just volume. So these are the quantities that we are after. We can just substitute them in the above place. Okay. Now that I will do that. So the determinant now would become first term is del H by del S at constant pressure. So you see del H by del S at constant pressure is temperature. So first term is temperature. Second term is volume. As you can see, del H by del P at constant entropy. So that is over here. It's a constant volume. Then remaining terms I'll just write as it is. We'll come to that little bit later so that it's easier. And so here it is inverse of del H by del S at P, right? So this is volume and inverse is 1 by V. So we will have 1 by V here, multiplication. Okay, so this is the first part. Now we need to figure out the other two things. So how do we figure that out? Let's first, yeah, first is we need del S. Okay, do you remember what is the formula for CP? Do you remember that? CP, do you remember? Is this the CP formula? Huh?
Yes, sir.
Then del T by del S constant P just going to be equal to, I'm just inverting this, then will be 1 by Cp, 1 by T, the T will go up, so T by Cp. Okay, so this is this term. Now we need another term. We need to find out, okay, I'll just keep this as 1 for now. This is 2. Then we need, what do we need next is del T by del P constant S. So this is a term that we need. So using Maxwell relation, this term comes out to be something like this. You check the Maxwell relation. So this is directly from Maxwell relation that I'm using this. Okay. Then we will use little bit of Jacobian transformation again to get some, to manipulate it and get the values that we want. Okay. I'm just writing it as a Jacobian. Then we'll use P and T. Okay. P and T. Here also P and T. Right. So again, we'll have to change a little, we'll have to invert it. So we see that again, will be minus V by P del T by P, T and P again it will be into minus del E, sorry, T and P, T, P, del SMP. So again minus minus will get cancelled. So this will become something like del V P and del T by del S constant pressure. So you see here again we have some known quantities. You remember isothermal expansion coefficient alpha. Alpha is equal to, what was alpha's value? Alpha is equal to 1 by V del V by del T at constant pressure, right? So then we have that over here. So basically this is going to be just alpha V. So this is alpha V. So this quantity alpha V into, and this is again the same as this quantity 2. So that is going to be equal to T by Cp. So we have our third value as well. Del T by del P constant S is equal to alpha V T by Cp. This will write as 3. So now we need to substitute 2 and 3 in 1. So 2 and 3 in 1. If you do that, what we will get? We'll get T V T by Cp alpha V T by Cp. Then outside we get 1 by, we get that. Oh, sorry, this is 1 by T. I forgot. This is 1 by T because delta H by delta SP is T, right? 1 by T. So outside we'll get 1 by T. So this is just basically a determinant, right? So we need to multiply these two minus that. So alpha V T squared divided by Cp, okay, minus Vt by Cp. Here will be 1 by T. So this T, this squared will get cancelled. We can take Cp out, V out as common. So it will be V by Cp alpha V minus 1. So that's what will be left with. So what is this? This is our new JT. Okay. So this is what we wanted, and this is the final formula of Joule-Thomson coefficient in terms of something measurable. Okay. I mean, you might think that it's long and all, but it's just simple transformations from through various thermodynamic quantities and using Maxwell relations and natural variables, Legendre transformation. So it's simple, but you just need to understand these basic concepts. All right.
Yes,
Do you have any doubt here?
I have some doubt in
Yeah.
this position number 2.
Number 2. Okay.
Yeah,
Here
yeah.
you have a doubt.
There in under the line, what you do, I can understand.
Sorry, I didn't hear you clearly. Where are you telling?
In
Two, this
second
one?
line,
Huh?
I have. In second line,
This one or this?
yeah,
Here, the negative sign. Jaydeep, which one are you talking about? Delta T by del P or Cp?
delta T del P.
Ah, that line. Okay. So this first transformation that I'm doing, so this is a Maxwell relation, okay? This is a Maxwell relation. So just check your class notes, it might be there. Yeah. So this is a Maxwell relation. Fine. Then I'm doing the Jacobian method of transformations. So this do you understand?
Yes, sir.
So then again, I'm just what I'm doing is I'm multiplying and dividing by del P del T. Okay, del P comma T. Fine. This part you understood.
Okay, sir.
So then
I
what I do?
understand.
Oh, okay. Then you understood then.
Yeah, yeah. Either
So then I'm just here it is PT. Then I'm making it TP. So that means I have to put a minus here. So then here again it is PT. I'm making it TP. So I have to put a minus there as well. That's why all these transformations. All right.
yes.
Okay. Now fourth question. Oh, sorry, fifth question. Read the question and tell me how we can solve it. This is quite straightforward. What do we have to calculate, JB? Okay, see, the internal energy of the gas is given by this formula. Okay, that is given. They are asking us to calculate the change in internal energy when this compression happens from 0.05 meter cube to some volume. They have not told us the volume, but we have to find the volume. And then they have given us the relation also. So P V power 1.4 is equal to constant. Okay. So since it's a constant, P1 V1 1.4 is equal to P2 V2 1.4. Now we need to find out V2 so that we can calculate the internal energy from there. So V2 power 1.4 is equal to P1 1.4 divided by P2. Okay, I'll just substitute the values. 1000 kilopascal to 0.05 meter cube 1.4 divided by 2000. So finally, you calculate and tell me how much this is?
7.54 into 10 to the power minus 3.
Okay, 7 point to the power 3. Okay, are you sure? Okay, 7.54
54.
to 10 power minus 3. Now you
Yes,
do the this also and tell me the volume. How much meter cube? Okay, coming to about 0.03 meter cube. Okay, this is the volume 2. Now we need to calculate the other values. Now we need to calculate internal energy. So the internal energy formula that they have given is how much? 7.5 7.5 PV minus 425 kilojoules. So this is what they have given us. Alright. Now what we'll do is we'll just first we'll write U1. U1 is 7.5 P1 V1 minus 425. U2 is 7.5 P2 V2. Correct. Minus 424. Now delta U is equal to U2 minus U1. We just need to subtract these two. So it will be 7.5 P2 V2 minus 7.5 P1 V1. And this 425 and 425 will get cancelled. That is quite simple. 2v2 minus v1 v1. So let's just substitute the values and find out. So here P is in 1000 kilopascals and V is in meter cubes. Let's maintain that. 2 is 1000 to 0.03 minus 1000 to 0.05. Correct. It's 0.5. How much is this coming to? So that is coming to 10. Therefore, delta U is equal to 75 kilojoules. Correct. Okay. Did you get this, Jyoti? Yeah. Hello. Hello.
Yes, sir.
Any doubts? Simple. It's simple arithmetic. Okay. Any doubts here?
No, sir.
Okay. Then we have this Carnot engine. Okay. So as you can see here, we have a Carnot engine. Okay. This is the engine. And what they're telling is there is a higher temperature, that is T1 output, that is equal to 800 Kelvin. And it's drawing some certain amount of heat Q1, and it is doing some work W, and it's releasing some heat, let me put it as Q2, to some temperature T. And this work is taken up, same amount of work is taken up by the refrigerator to, and then that refrigerator takes up heat T, let me put it as T2 from 280 Kelvin to 80 Kelvin, and then puts heat, transfers this heat to a reservoir T. And what they're telling is the when the heat is given to engine is equal to the heat absorbed by the refrigerator. That means this heat absorbed by the refrigerator is equal to this heat. Okay, and then W is also equal, and this temperatures are also equal. So these are the things that they have already told us. Okay, now they're asking us to determine the efficiency of the engine. So the efficiency of the engine formula, simple, right? 1 minus T, here it is T, cold temperature is T by T1. This is what we need to find out. For that, we need to find out T. Okay. So what we have to do is we have to find out this T value. Since this T value is common for both the engine and the refrigerator, we can somehow equate these two via work, which is also equal, to find this temperature. So that is our idea now. Okay. So now let's see, since work is the same, this work done by the engine is taken up by the refrigerator. So we'll equate the work. First, let's find the work done. Okay. Eta, which is equal to 1 by T by T1, is also equal to what? Work done by the heat input. No? Heat input is Q1. So which implies work done is equal to Q1 into 1 minus T by 800 Kelvin. Okay, fine. So this is for the engine. Now we need to find the work from refrigerator's perspective. Now let's do that. So what is the refrigerator's thing? So refrigerator, if you see, we have the coefficient of performance, right? Their coefficient of performance of cooling is equal to Q1 by W. Fine. And also we need to find, which implies W is equal to Q1 divided by coefficient of performance. And this coefficient of performance also has another formula. Coefficient of cooling, performance of cooling is equal to the cold temperature divided by hot temperature by cold temperature. Here the cold temperature is how much? 280 Kelvin, no? And hot is T. So this is 280 divided by T minus 280. Now we'll substitute that in this work. So now work is equal to Q1 divided by 280 divided by 1. So which is equal to what? Q1 T minus 280 divided by 280. So we'll get this. So we have work from refrigerator and work from engine. So both these are equal. So we'll just equate them. So work engine is equal to work refrigerator. So from 1 and 2, 1, 2, let's equate them. So Q1 minus T by 800 is equal to Q1 T by 800, 280 divided by 280. So this Q1 and Q1 are equal, they'll get cancelled. Now we just need to simply cross multiply from arithmetic by 800 equal to T by 280 minus 1. So it will become what? This goes that side. So T is equal to T by 800 plus T by 280, which is this time. So this is equal to 280T plus 800T divided by 800 to 280. Okay. 2 into 800 0 plus how much is this? We just calculate it quickly. This is coming out to be around 414.81 Kelvin. So this is the cold temperature for engine and also the hot temperature for refrigerator. Fine. Did you understand this part, JD? What I have done
Yes,
here?
sir.
Okay. Now we need to calculate the efficiency of the engine, right? So that is simple. 1 minus T by T1 that is equal to 1. 414.81 divided by 800. And how much is this coming out to be? 0.48. Okay. So it is 48% efficient. Okay. Did you understand this?
Yes, sir.
Okay. Then if you understood that, let's go to the next question. Simple actually. So now they're telling consider a system with energy levels. 3 energy levels are there. First energy levels is 0, then second energy level epsilon, and also but it's twofold degenerate. So that means there are two equal degenerate states over there. Sorry, yeah, degenerate states over there. And then other two are some different. They have only single states. Okay. So now they're asking us the partition function of the system of this system. So how do you calculate the partition function? Can you tell me the formula? Do you remember? For sigma I e power minus energy I divided by kBT. Do you remember this?
Yes, sir.
So that's what we have to use. Here 1 by kBT is beta. I'll just write it as beta. Right. This is the formula. So we need to write it like this. The partition function for the system is going to be equal to minus beta. First energy level is energy 0, right? So we'll just put the 0 plus second energy level is epsilon, but it has 2. So multiply it by 2 minus beta epsilon plus epsilon minus beta to 2 epsilon. So this is 1 plus 2 beta epsilon plus minus 2 beta epsilon. Okay. So this one actually is like a quadratic formula. Okay. So I'll just do it. Yeah, I'll just write it. See, this one can also be written like this. Okay. Beta epsilon whole square. Anyway, this is going to get multiplied, right? So it's like a quadratic formula. Beta epsilon square. This is the Q system. This is the partition function of this given system. Okay. Fine, Jaideep. Did you understand that?
Yes, sir.
Okay. Now we need to find out a similar problem, but okay. Now what are they telling us? We have system has energy levels uniformly spaced like this. Okay. Change this one. Control. Okay, space like this. So that means the delta E between systems 3.2 into 10 power minus 20J. So let's assume E naught is equal to 0, which means E1 is going to be equal to 3.2 into 10 power minus 20J, which is nothing but delta E, 1 delta E. Then E2 is going to be equal to twice of this, okay, 2 delta E. Then E3 is going to be equal to 3 delta E, so on and so forth. So that's how it's going to be equal to. So which implies energy of any given level is going to be equal to N delta E. Fine. So this is our formula. So we need to find the partition function for this system. So Q is equal to, again, let's write it out. I e power minus, I'll write it as beta only, beta EI. Now what is EI or EN? Maybe I'll write it as N so that it's consistent. This is actually similar to a problem we did 2 weeks back. Okay. So sigma N e power minus beta N delta epsilon. So what is that? It's going to be equal to e power, first one, it is 0, no? E naught is 0. So that's going to be equal to minus e power 0 plus e power minus beta delta E, 1 only. Second, it will be 2, na? So 2 beta delta E and epsilon. Then it will be minus 3 beta delta epsilon, so on and so forth. Okay. So this is 1 plus e power minus beta delta e plus e power minus 2 beta delta e, so on and so forth. So now, do you remember 2 weeks back we spoke about the formula like this: squared plus x cubed plus, till if it goes till n, it will be 1 by 1 minus x. Do you remember this formula?
Yes, sir.
Yeah, you remember this, right? Yeah, that's the same formula that we are going to use here. Therefore, partition function is equal to 1 divided by 1 minus e power minus beta delta e. So this is our formula. Okay. So we have the partition function. We have the partition function. Now, why did I calculate the partition function? What is the question? Question was where they are asking what fraction of particle is in the ground state at t is equal to 0. That means what is the fraction of particle that is present when energy is 0, right? So how do we calculate that? What is the probability? How do we calculate? P0, how do you calculate? E power minus beta epsilon naught divided by q. So this is the probability. So that is why I was calculating all these things. Correct. Okay. So
Yes.
e power, this is minus beta 0, na? E naught is 0. So divided by q only. So this is just 1, simply 1. So this is 1 by q. So what is 1 by q? It is inverse of this. So that is by e power minus beta delta epsilon. Okay. So now we need to calculate this value at 300 Kelvin. 1 minus exponential of beta is kBT. Okay. So delta E is how much? 3.2 into 10 power minus 20. Beta is 1 by kBT. So we will have Boltzmann constant 1 by, okay, maybe. So this is basically what? E power minus delta epsilon naught divided by kBT. Okay. This is what it is. That's what I'm doing here. 10 power minus 23 into 300. So let's calculate this value now. It will be better. We can simplify it more. Sure. I can just like this. It will become 10 power minus 3 by 2 divided by 1.38 divided by 1.38 into point. How much is this? Let's see. Power divided by 0.3. Sorry, minus, I forgot the minus. Okay. So this value is coming out to be something like this: 0.9996. So basically, most of the particles will be in the ground state at this temperature. Probably 4 out of 10,000 particles can go to some other state. Do you see how probable higher order states are, right? It's really less probable. Okay. All right. Did you understand this, Dedu? Any doubts?
Can you explain again?
Okay. I'll explain it again. So which part you didn't understand? The partition function part or probability part?
Probability.
So you understood how I'm calculating partition function, right?
Yes, sir.
Okay. So the probability of any given state, okay? So let's say any given state, it's actually the energy of that state, okay? Weighted by the probability, weighted by the partition function. So this is the formula actually. E power minus beta epsilon naught by q is the formula. So here, since it's the energy is 0, it's just going to be 1. 1 by q, that's what we have got here. 1 by q. So this is q. 1 by q is just 1 minus e power minus beta delta e, right? Do you understand this?
Yes, sir.
Okay. So then after that, all these is just mathematical. I mean, this is simple arithmetic. So that you can do. So what I mean by having such a high probability, so basically this is a very high probability. So that means out of you know 10,000 particles, 9996 particles will be in ground state. Okay,
Okay, sir.
only 4 particles can go to some higher state. So that means ground state is the most probable state at 300 Kelvin for this system. Okay, did you understand that?
Yes, sir.
Okay, and if you understood that, then we'll go ahead to the next problem. Next problem is okay. This is again a simple transformations. Okay. Um, so here in the question, if you see, they are asking everything in terms of the options are in terms of isothermal compressibility, terms of KT. We have to get it in terms of KT, kappa T, not KT, kappa T, isothermal compressibility. So this is what you have to do. So now, if you see, what we need is what is the formula for isothermal kappa T is equal to what? Minus 1 by V, then del V by del E, constant temperature. Correct. So this is the isothermal compressibility. So we need something in on this lines. So we have to transform this del Z by del V to something like del V by del P. So that's what we are going to do now. Okay. What we'll do is we'll write it. We'll use Jacobian to transform that. Del E comma T del what am I going to do is I'll multiply and divide by PT. Okay. T multiply and divided by PT. Okay. That's what I'm going to do. And then we'll exchange them. Then it becomes after that is straightforward. Del Z by del at constant temperature. Del P by del P at constant temperature. We can further write it like this. Del G by del P constant temperature 1 by del V by del P constant temperature. So this we can write. So now if you see Gibbs free energy equation, this value, this is actually del G. You see the Legendre transformation of Gibbs free energy equation. This is nothing but volume. Okay, so we'll have volume here. Then this, okay, we have del V by del P. Here also del V by del P. So this is basically equal to minus KTV, right? And it's in the denominator. So it's going to be 1 by minus kappa T V. So the final answer, okay. Therefore, del G by del T temperature equal to minus 1 by kappa T. So this is the final answer. Okay. Did you understand that?
Yes.
Okay. So then this is the last question that you actually asked. So what we have here is, see, this, okay, first thing is, do you know about microcanonical ensemble? Do you know what do you mean by microcanonical ensemble? No, okay. See, the Boltzmann distribution that Sir taught in the class, that is canonical ensemble, where the population is based on weighted averages. But in microcanonical ensemble, all the all the states are equally probable. Okay, all the states have equal energy and they are equally probable. There is no difference there. So basically, let's say this ensemble has 100 states. All 100 states have equal probability. Fine. So that is what they mean by microcanonical ensemble. All right. So because this is microcanonical ensemble, let's say there are n number of states. P1 is equal to P2 is equal to P3 is equal to, like that, till Pn, okay, is equal to 1 by n. So this is the probability of all the states. All of them are equal. All right. So now what we need to find out is, we have energy, total energy in this ensemble is 4 epsilon. Okay. Total energy is equal to 4 epsilon. And then number of atoms is equal to 12. And they are telling energy can either be energy either 0 or epsilon. Nothing 2 epsilon, 3 epsilon, nothing like that. Okay. So basically, one atom, any given atom, it can be either 0 or epsilon. So that's what can happen. And remember that all the states have equal probability. So because all the states have equal probability, in all states total energy is going to be 4 epsilon. So that is set. Now, out of these 12 particles, you choose 4 particles and then give them 1 epsilon energy. So that way you will get 4 epsilon. Remaining 8 particles will have energy 0. This, do you understand this part?
Yes, sir.
Okay. So basically then number of states, what it will happen is, so total number of states W is just going to be based on the number of ways you can choose 4 particles out of 12 particles. Correct?
Yes, sir.
So what is the formula for that? You're choosing 4 particles out of 12. Now, what is the different number of, how many ways can we do that? 12C,
4.
12C4. Correct. Yeah, that's all. So now let's do that. We are doing 12C4. That means
495.
W is equal to how much? 12 factorial divided by 8 factorial 4 factorial
495.
495. Okay, 495. So that is the number of microstates. Okay. Then what is the entropy? Kb ln W, right? So Kb ln 495. What is the value for this? Therefore, entropy is equal to, how much is this daily?
6.20 kb.
6.20 kb. So that's the value, that's the answer. Okay.
Yes.
Okay, Jaideep. So those are the questions that I had prepared. Now we will see what are the questions what are the questions that you had that have been already answered. So let's go to that. So you wanted to see other questions, right? Let me check all the other questions. Okay. So okay. So first question, which question? Third question, right? Hello.
Yes, sir.
Third question, it's actually a little tricky, but it's a simple question, okay? So what they're telling is there is a membrane and it melts at a melting temperature 41 degrees Celsius. And some reversible melting experiments show that delta HM melting enthalpy is 9 kilocalorie per mole. They're asking us the Gibbs free energy, okay? It's tricky question because important thing to note here is a reversible process, okay? Fine. It's a reversible process, so that means it is at equilibrium. So at equilibrium, the Gibbs free energy is equal to 0. Fine. Okay.
Yes, sir. Yes.
That is the answer. Okay. Now, what is the next question that you asked?
4.
4. Okay. So we have reversible heating of 5 moles of liquid steam to. Okay. All right. So first, let's talk about work. It's a positive or negative. It's simple, okay? So basically, you're converting water to steam. So that means volume is going to expand. Correct. Water is liquid. This is gas, no? Its volume is expanding.
Yes, sir.
So when volume is expanding, what is the work? Delta V is positive. So work is minus P delta V. Correct.
Yes, sir.
So W is going to be negative. So that is there. W is negative. So then how do you calculate the Q is the next question. I'll show that. Let me show that. What I'll press on. Okay, let me just press on my test so that it's easier. Huh. So what we'll do here is, see, we have 5 moles, some question 11 put. We have 5 moles of water.
Sir, I cannot see.
You cannot see. Okay. Can you see now? Yeah, I think you can see. You can see my screen, right?
Yes, sir.
So basically 5 moles of water in liquid phase is going to 5 moles of H2O in gas. So that's the thing. So now what is the Q is what they're asking. It's simple actually. So number of moles, okay, or now I'll just put H2O. Number of H2O into latent heat of vaporization. Okay. So what we need is latent heat of vaporization value. Now we have 5 here. Let's go and calculate. I'll check the value here. I have noted it down anyway. The latent heat of vaporization is 9.7 kilocal per mole. That's the value it's given. So then after that is just simple multiplication. So how much is that? 48.5 kilocal. So that is a Q. Okay. So there's something called latent heat of vaporization when there is a phase change happening. Okay. So that's what you need to consider and work out over there. All right.
Yes, sir.
Okay. Then what is the next question that you asked?
12.
12. 12. Okay. So 12 is it's a direct formula. Okay. You check your notes for ideal diesel engines value. It's there in the note. Okay.
Okay.
Then next
16.
16. Okay. So
Did
again, I
you tell?
sorry.
You told in in your notes. You told. Yeah.
Yeah, 16 also is there. It's simple actually. It's depending on the Clausius, whether the Clausius statement of second law of thermodynamics is violated or not. You have to check that. Then it's quite straightforward.
Yes.
Okay. Then anything else?
9.
19. 19 we solve this right now.
Yeah.
Yeah. Then anything else?
25.
25. 25 it's a little bit tricky and long process. Actually, what you have to do is you have to take the van der Waals equation of gas, and then you have to differentiate v with respect to t, and then you have to differentiate v with respect to p, and then this way you will get the answer. Okay,
Okay.
you try that. Then anything else?
And 30.
30 again we discussed, no?
Uh,
No problem.
yeah. Yeah.
Yeah, that's it. All right. Are you giving this exam?
Yes, sir.
Okay. So all the best for your exams
Thank you, sir.
and good luck with your studies.
Yes, sir. Thank you, sir.
Okay. Thank you.